So hello and welcome back to another video in a geological series. I have no idea what series it is, but anyway, in this video we're looking at granite and rhyolite. So you're probably going, two different rocks, why are you actually putting them together? Well, basically in the mineral and chemical series, granite and rhyolite are treated as equivalents, but granite actually forms under the ground. So this one forms in mostly batholiths from Plutons, and the rhyolite forms extrusively. So this actually come out as a lava, and most likely is that this was formed as an ash, so a volcanic ash, which would have come out. You see the smoke. It's better off if I actually draw an actual picture. So pictures are good. This is how I learn. Me reading actually doesn't do me that much good. So you got actually the volcano. So I don't know. This is probably actually more like probably a composite volcano. It's too steep actually. Volcanoes usually more like that. And then you've got the caldera. You've got the smoke that comes out. So you got all the pumice and scoria that actually falls down here. So that's has a lot of vesicles, but we're not talking about that. And then you've got the ash. So the ash actually can go a hell of a long way. So this is the ash. And then that rains down on a different area. So got another hill there. The ash actually rains down. And then, so we've got the neck, and here we have the Pluton. So that is actually, Pluton. That's when it's molten. So molten. And a batholith when it solidifies. Volcanic neck. And there's the plug. And here, you have different layerings. So if we see in this one, we have actually different layerings of the actual rock. So you can see there, it forms a bit like a sedimentary rock, not always. As we see in this one looks like it's pretty massive, although you can probably see some layerings on there. And that's actually basically either a fine type of silt, the structure, so fine particles, or it's a volcanic glass. So if you put it under a microscope, you can probably find looks like glass. But if we zoom in, this camera actually doesn't zoom in, and actually the pixelation actually decreases. But you can see it's very fine. And so a lot of people can actually get this confused with actually sedimentary rock. Because actually it does look like a type of sedimentary rock. It looks like a siltstone. So here I actually have a siltstone. And maybe looks similar. This is probably a little bit coarser. So probably does have some sand in it. But then you need to actually do a chemical analysis. They're expensive, so I wouldn't recommend it. Use geological maps, or get these from a reputable site that actually does specialize in geological material. So these ones I got, probably got like 25 years ago when I done geological course. So these are actually certified as the correct mineral, correct rock, should I say, with the correct minerals. And so this is actually a granite, and you can see the large crystals because this would have solidified over hundreds and thousands of years. This one would have solidified quite quickly. And sometimes when a rock or where ash falls on the ground, they can actually recrystallize. That really hasn't happened here. But the difference is that this one actually has they both have potassium feldspar. This one's usually sanidine, should I say, and that is usually a high temperature form of potassium feldspar. This one has most likely orthoclase, which is a low temperature, a microcline orthoclase, so that they have a different structure in their crystal system, but we're not going to worry about that at the moment. So what actual minerals can you find in the actual rock? So if we, well, first here I've done the actual, so sanidine has monoclinic structure, and two angles are actually right angles. In microcline, they're not right angles, they're all different angles. So this one you can have a centered, cube centered structure, so you've got an atom in the center. This one's just a primitive, which is also primitive as well, but maybe I'll do a video after I've actually learned that a hell of a lot better. So in rhyolite and granite, we have orthoclase, so that usually makes up about 50, roughly like that. So orthoclase. Then you've got plagioclase feldspars. So these are chemical formula for orthoclase. So potassium, aluminium, silicon, oxygen. Plagioclase got sodium and calcium. And as you can see, the end members are actually the same. But usually in the earlier rocks, in the lighter rocks, we have more sodium. In the darker rocks, we have more calcium. So calcium-rich end members and sodium-rich end members. So in plagioclase feldspar, and that can make up like 15 in granite to about 20%. Something like that. They do vary. Then we have quartz, and quartz can makes up about 20%, 20 to 60. And then we got muscovite. So quartz is just silicon dioxide. Then we have muscovite and biotite mixers. So these are actually sheets. When you actually look at a rock, you can actually find if it has a sheet and it reflects. They're actually quite easy to actually see. So muscovite is calcium, aluminium, does have fluoride, and a biotite generally has magnesium and iron. So that's mainly the differences. And if you have a look at here, we have F and OH, so these never occur together. So even though the muscovite might have this chemical formula, and also the calcium and aluminium, as you can see, sorry, I shouldn't have done that. So only the fluoride and the hydroxide doesn't occur together. The calcium aluminium does. So, and the same with these ones as well. So when you've got a comma in between, it means you have only one of these elements. So in biotite, you can have magnesium or iron. You can't have both together in the same crystal structure framework for that. For like a crystal structure like this. So you only have one of those atoms. You don't actually have both of these atoms together. But they can occur in the same crystal, so I was a bit wrong before. It's just a little bit hard to explain, so I'm not going to explain it any further. Then we've got hornblende. So this is actually a more complex structure. As you can see, a lot of different elements go in hornblende, which is an amphibole. So if you actually turn the light on, oh, it's already on. Look at the actual crystal structure. We have actually quartz. It's like a smoky quartz, and that's because it has free aluminium and silicon. Then we have the white. That is the plagioclase. And the potassium feldspars. So because this is actually granite, it has more orthoclase and plagioclase. So the orthoclase is the potassium feldspar, and it can actually make the rock pink. So here we have the potassium feldspar, and we have the colors that actually comes in. So it comes in colorless, greenish yellow, white, and pink. So if it's pink, then it's most likely a potassium feldspar. And the plagioclase, usually white, grey, bluish white. So if it's white in color like here, it's a bit hard to tell which one is actually more predominant. But as we have a lot of amphibole, it's more likely towards the plagioclase end. So that's why it actually is more white. And here in the other granite, you can see it's actually pink. So pink color. So indicates it's probably a potassium feldspar, because it's plagioclase feldspar doesn't have pink. And we have a lot of quartz. You can see here. So let's zoom in. So we have a lot of quartz, and we only have a small amount of biotite. So biotite, and I don't see that much muscovite. I don't see any muscovite really. So, and a muscovite, and also the hornblende is actually not that much. So this rock here actually has a lot more hornblende in larger crystals. There's a large crystal hornblende there. The muscovite is actually also a bit smaller. So can we see any muscovite or biotite micas in here? So I need to actually get a reflection. No, it's not going to work today. Damn. Maybe if I can actually change the light source. So you just turn it around and you try and look for an extinction. So that's when the light actually disappears and goes sparkly, sparkly. And no, I'm not really getting anything. So maybe it's most likely going towards the granodiorite end member. Oh, not end member, type of rock. But it does have a lot of silicon. A lot of quartz. Definitely a heap load of amphibole. Oh. And potassium and Plagioclase Feldspars. Beautiful. So it looks like we have some, looks like there. That would be the actual muscovite. It looks a bit silverish. Some more there, but it's actually pretty hard. The muscovite's actually quite small. So, and in this one, as you can see, it's actually pinkish in colour. There's a minor amount of hornblende. There should be muscovite and biotite micas here, but you can't actually see them that well. So if you're not too familiar, this is actually smoky quartz. This is the feldspars, potassium feldspars most likely, hornblende, and yeah, you need to get a greater magnification to actually get a look at any of the biotites or the muscovite micas, but they're very distinct when you actually pick them up. As I said before, they're flat sheets. So anyway, and then we got this one. As you can see, it's, as I said before, it's very fine grain. These are actually less than a millimeter in diameter, but these are actually the same. And the reason why it looks white is because of all the actual silicon, feldspars and quartz that are actually in it. So they can actually drown out the actual darker muscovite, biotites and hornblende. And actually it makes it look a bit muddy. So that's very interesting to actually find that. So when you're actually out in the field and you actually see these type of rocks, look on the geological map and you should be able to pick it up straight away. And you also have the internet, so just research what type of rock that would actually look like. Most of these rocks look pretty similar, although as we see with the granites, you get pink and white, so it's a very interesting color. So here we have the QAPF diagram. So amphibole, plagioclase, orthoclase, quartz. And as you can see, granite is here, so is rhyolite. So we have 20% to 60% quartz. Then we have 65 to 10% plagioclase. So these numbers represent the quantity of plagioclase. And as you can see, we don't have to worry about the feldspar oids down below because they actually are not in granite or rhyolite. And here we actually have the chemical composition. So these are the minerals actually in it. So we've got rhyolite, granite, plutonic, volcanic. So and there we have the equivalent with Avarox as well. So with granite, we're talking roughly about here and lower. So probably roughly, I would say here. So as you can see, plagioclase is, I don't know, 15 to 25%. Then we've got quartz, roughly 20%. Can be up to 60%. Orthoclase, as you can see, orthoclase, which is the potassium feldspar, decreases and gets extinct around a granodiorite. Then we've got muscovite, so they've got two micas here, which I don't know, roughly equivalent, 50-50. Then we've got hornblende, amphibole. So hornblende is actually part of the amphibole group. And as you can see, it's, you know, probably 6%, and then it goes up to 12 to 13%. So it actually should get darker as it progresses towards granodiorite. And as well, I'll show you just the granite diorite, the differences between granite and granodiorite. Oh, gee man, good. I ripped the bag. Now it's very hard to bloody open. Damn. Go, go. So here we have the granodiorite. So here we are. You have the granodiorite, we have the granite. And as you can see, this one looks more like salt and pepper. So it has a lot more amphiboles. Definitely a lot more plagioclase. So you see the plagioclase is white, grey, bluish white. And the quartz actually decreases, and so does the orthoclase, which is also a lighter colour. But that's very interesting. So anyway, let me know what you think of my video. If it's a bit boring, maybe I have to lighten it up and make it more entertaining. Anyway, thank you very much and have an awesome geological time.